In the summer of 1960, a young archaeologist named Mary Leakey knelt in the dust of Olduvai Gorge in Tanzania, brushing sediment away from a scatter of broken animal bones. Mixed among them were crude stone tools, chipped and battered, clearly shaped by human hands. The bones themselves told a story. They bore cut marks, thin scratches left by stone edges dragged across flesh. Something had butchered these animals. Something had eaten here, but the sediment held no charcoal, no ash, no trace of any fire. Whatever had killed and processed this meal had eaten it raw, and those cut marks were nearly 2 million years old. What nobody knew at the time was just how long this raw chapter of human history actually lasted. We tend to think of fire as something humans always had, like it was built into the starter kit. But the reality is that our ancestors walked the earth for well over 2 million years before anyone figured out how to reliably start a flame. That is not a brief phase. That is the vast majority of human evolutionary history. And during all of it, every single calorie that entered a human body went in uncooked. So what did they actually eat? And how did they survive on it? The East African savanna, roughly 2 to 3 million years ago. Picture a landscape that looks something like the modern Serengeti, but wilder, with patches of dense woodland breaking up wide stretches of grassland. The climate was shifting, forests were shrinking, open spaces were expanding, and a small, upright primate was being forced out of the trees and onto the ground. This is where the story begins, not with a single species, but with a whole lineup of early hominins, creatures that were not quite apes and not quite human, spread across the African continent. Australopithecus, Paranthropus, early Homo. They were short, they were vulnerable, and they were surrounded by predators that were faster, stronger, and far better equipped to kill. They had no fire. They had no weapons worth mentioning. What they did have were hands that could grip, teeth that could grind, and a growing knack for figuring things out. The foundation of the pre-fire diet was plants, fruits, leaves, seeds, flowers, bark, and especially underground storage organs. That is the scientific term for tubers, roots, corms, and bulbs, the starchy structures that plants use to store energy underground. Think of a wild yam or a tough, fibrous root buried half a meter in hard-packed soil. These were calorie-dense compared to leaves and far more available than meat. They were also a nightmare to eat. Raw tubers are tough. They are fibrous, gritty, and often laced with bitter compounds that plants evolved specifically to discourage animals from eating them. Some species contain toxins like tannins and cyanogenic glycosides that cause nausea or worse if consumed in large quantities. Our ancestors had to learn, probably through painful trial and error over generations, which tubers were safe and which would make you sick. Chewing through a raw wild tuber is not like biting into a potato from the grocery store. It takes serious jaw strength, and it takes time. Researchers estimate that early hominins may have spent 5 to 6 hours a day just chewing. That is not a typo, by the way. Half the waking day, grinding away at raw plant material just to extract enough calories to survive. Getting to these tubers was its own challenge. The underground storage organs of many African plants sit 20 to 50 centimeters below the surface in soil that bakes rock hard during the dry season. Modern chimpanzees do not dig for tubers. They lack the patience and the tools. But early hominins developed simple digging sticks, probably sharpened branches, and used them to pry these calorie bundles out of the ground. It was backbreaking labor, and it required mental maps of the landscape, knowledge of which patches had been dug recently and which had recovered enough to be worth revisiting. This was not mindless foraging. It was planned, strategic, and deeply dependent on accumulated knowledge passed between individuals. This is partly why early hominin skulls look the way they do. Paranthropus boisei, sometimes called Nutcracker Man, had enormous flat molars and a pronounced sagittal crest on top of the skull, a ridge of bone where massive chewing muscles attached. That skull was essentially an eating machine, purpose-built for processing the toughest plant foods the African landscape could throw at it. Fruits were easier when they were available. Wild figs, berries, and the fleshy coverings of various seeds provided quick sugar and energy. But fruit is seasonal, unpredictable, and every other animal in the forest wants it too. Early humans were competing with baboons, birds, and insects for every ripe fig. You could not build a reliable diet around fruit alone. Seeds and nuts offered more concentrated energy. Cracking them open was the challenge. Some researchers believe that the earliest use of stone tools was not for butchering meat, but for smashing open hard-shelled nuts and tough seed pods. A flat rock as an anvil, a round rock as a hammer, and suddenly you have access to calories that were previously locked away inside protective shells. But plants could only take our ancestors so far. And this is where the story takes a turn nobody expected. For decades, the popular image of early humans was the mighty hunter, a spear-wielding predator stalking big game across the savannah. That image is mostly wrong, or at least wildly premature. Long before our ancestors were capable hunters, they were scavengers, and not particularly glamorous ones. Imagine a group of early Homo habilis on the open grassland, maybe 6 or 7 individuals, watching from a safe distance as a pride of lions brings down a large antelope. The lions eat their fill and eventually wander off. Then the hyenas move in and strip more meat from the carcass. Then the vultures descend. And only after all of those more dangerous animals have had their share, our ancestors creep forward with their crude stone tools, looking for whatever is left. This is called passive scavenging, and the evidence for it stretches back roughly 2.5 million years. At sites like Olduvai Gorge and Kubi Fora in Kenya, archaeologists have found animal bones with a very specific pattern of marks, stone tool cut marks overlaying tooth marks from large carnivores. That sequence matters. It means the carnivores ate first, and the hominins came later, slicing off whatever scraps of meat and sinew remained. It does not sound heroic, but it was genuinely dangerous. The African savanna, 2 million years ago, was crawling with predators. Saber-toothed cats, giant hyenas, leopards, and wild dogs all competed for the same carcasses. Approaching a kill site meant risking an encounter with an animal that could kill you in seconds. Our ancestors had to develop acute awareness of their surroundings, reading the landscape for signs of danger, watching the sky for circling vultures that signaled a fresh kill, and making rapid group decisions about whether the reward was worth the risk. Over time, some researchers believe passive scavenging gave way to something bolder. Power scavenging, or confrontational scavenging, is the idea that groups of early humans learned to drive predators away from fresh kills using coordinated yelling, rock throwing, and sheer numbers. A group of 10 or 15 hominins charging a pair of cheetahs on a fresh kill, screaming and hurling stones, might have been enough to claim the carcass before most of the meat was gone. This is speculative, but it fits the evidence. Some archaeological sites show hominin cut marks underneath carnivore tooth marks, which means the humans got there first and the carnivores came later. Either way, scavenging was a turning point, because even those scraps of raw meat provided something that plants could not: dense, concentrated protein and fat. Pound for pound, meat delivers far more calories than leaves or tubers, and the protein contains amino acids that are essential for brain development. Our ancestors were not choosing meat because it tasted good. They were choosing it because the ones who found it survived at higher rates than the ones who did not. Evolution does not care about table manners. And then there was the real prize, the thing that set human scavengers apart from almost every other animal competing for carcasses: bone marrow. After the lions and hyenas had stripped a carcass clean, there was still an enormous reservoir of calories locked inside the long bones. Rich, fatty marrow that no other scavenger could access because no other scavenger had the tools to crack those bones open. Hyenas could crush some bones with their massive jaws, but the largest, thickest bones defeated even them. Our ancestors figured something out. Pick up a heavy rock, bring it down hard on the midshaft of a femur, and the bone splits open to reveal a dense core of golden, oily marrow. This was not just food. This was a unique ecological niche, a calorie source that early humans had almost entirely to themselves. Archaeologists call it the marrow niche, and some researchers believe it was the single most important dietary strategy in all of human evolution. The evidence is striking. Sites across East Africa from this period are littered with bones that show a very specific kind of breakage, the percussion marks left by deliberate, targeted hammerstone strikes. These are not random fractures from trampling or weathering. They are concentrated at the midshaft, exactly where you would strike to access the most marrow. And alongside these bones, you find the hammerstones themselves, rounded cobbles with battering marks that match the impact points on the bone. At the site of Kangera South in Kenya, dated to roughly 2 million years ago, researchers found thousands of bone fragments bearing these percussion marks, alongside Oldowan's stone tools and the hammerstones used to break them. The sheer volume of processed bones at some of these sites suggests that marrow extraction was not an occasional lucky bonus. It was a deliberate, repeated, and central feeding strategy. The caloric math makes it obvious why. A single kilogram of bone marrow contains roughly 7,800 calories. That is more than 3 times the caloric density of lean muscle meat. For a small hominin weighing maybe 40 kilograms, a couple of long bones worth of marrow could provide a full day's energy needs. And unlike a fresh kill, marrow stays viable inside intact bones for days or even weeks after the animal dies, long after the soft tissue has been consumed by other scavengers or rotted away. Our ancestors could return to old kill sites and still find calories waiting inside the bones, which, looking back, was either incredibly brave or incredibly stupid. Here were these small, relatively defenseless primates, squatting next to a carcass on the open savanna, surrounded by the smell of blood, hammering away at bones, while every predator within a mile could hear them. Speed was everything. Get in, crack the bones, scoop out the marrow, and get out before something bigger showed up. Brain tissue was another target. The skulls of large animals could be smashed open to access the brain, which is extremely rich in fat and docosahexaenoic acid, a specific omega-3 fatty acid that is critical for neural development. Some researchers have pointed to this as one of the great ironies of human evolution. Our ancestors ate brains to grow brains. But meat and marrow were never the whole story. There was another protein source that our ancestors relied on far more consistently, one that rarely makes it into the dramatic cave paintings or the museum dioramas. Insects. Modern chimpanzees spend a surprising amount of time fishing for termites, peeling bark to find beetle larvae, and raiding wild beehives for honey and bee brood. Given that humans and chimpanzees share a common ancestor, it is almost certain that early hominins did the same. Termite mounds are abundant across the African savanna, and a single large mound can contain millions of insects. Termites are roughly 35% protein by dry weight, and they contain significant amounts of fat, iron, and zinc. And no, I am not making that up. Termites are genuinely one of the most nutrient-dense foods available in the wild. A handful of them delivers more protein per gram than a handful of cooked beef. Our ancestors did not need to hunt them. They did not need tools, though simple sticks helped. They just needed to know where the mounds were and when the conditions were right for harvesting. Grubs and beetle larvae were another staple. Rotting logs and the underside of loose bark harbor fat, pale larvae that are almost pure fat and protein. Modern hunter-gatherer groups in Africa, Australia, and South America still eat these as a regular part of their diet, and they describe them as tasting rich and slightly nutty. Early hominins would have encountered them constantly while foraging in woodland areas. In fact, some paleoanthropologists suspect that turning over rocks and peeling bark in search of grubs may have been one of the first systematic food extraction behaviors, predating even the earliest stone tools. The sheer variety of edible insects available on the African savanna is staggering. Caterpillars, locusts, crickets, ants, and dozens of species of beetle all provided protein that was available year-round, unlike seasonal fruits or migratory animal herds. During locust swarms, which still occur across parts of Africa today, the calorie density per square meter of ground would have been off the charts. Our ancestors could have simply walked through a swarm, grabbing handfuls of insects and eating them alive. It sounds unpleasant by modern standards, but in a world without refrigerators or supermarkets, a locust swarm was a feast. Honey deserves special mention. Wild honey is one of the most calorie-dense foods in nature, and getting to it requires problem-solving, tool use, and a willingness to get stung repeatedly. Modern Hadza hunter-gatherers in Tanzania consider honey their most prized food, and they will climb 15-meter-tall baobab trees to reach wild beehives. Traces of beeswax have been found on stone tools dating back tens of thousands of years, though the practice almost certainly goes back much further. This next part is the one that has rewritten some old assumptions. For a long time, researchers assumed that aquatic foods played a minimal role in early human diets. We were savanna apes, the thinking went. We ate what the grasslands and woodlands provided, but the evidence from coastal sites in South Africa has challenged that picture significantly. At Pinnacle Point, overlooking the Indian Ocean near the town of Mossel Bay, archaeologists found shellfish remains dating back approximately 164,000 years. Piles of empty shells from mussels, limpets, and other marine invertebrates deliberately collected and brought to a cave for consumption. These are some of the earliest known evidence of systematic coastal foraging by humans. Shellfish are almost absurdly easy to eat. They do not run away. They do not fight back. They are packed with protein, zinc, iodine, and omega-3 fatty acids. Collecting them requires no tools, just the knowledge of where to look and when the tides are right. For early humans living near coastlines, shellfish would have been an almost absurdly reliable food source compared to the unpredictability of hunting or scavenging on the savannah. There is also evidence from Eritrea and the Red Sea coast suggesting that early human populations were exploiting shellfish beds as far back as 125,000 years ago. Along the Mediterranean, similar patterns appear at multiple sites. The consistency of this evidence across different continents and time periods suggests that coastal foraging was not a quirky regional strategy. It was a widespread human behavior wherever coastline was accessible. Some researchers have taken this further with what is called the aquatic ape hypothesis, though that label is misleading, and the idea has been largely reshaped into something more modest. The coastal foraging hypothesis suggests that access to marine and freshwater foods, including shellfish, fish trapped in tidal pools, and aquatic plants, played a much larger role in human brain evolution than previously recognized. The omega-3 fatty acids found in these foods are precisely the ones needed for neural development, and coastal environments would have provided them in abundance. Fish trapped in shallow tidal pools after the tide retreated would have been easy to catch by hand or with simple barriers. Freshwater streams and lakes offered crayfish, frogs, and turtle eggs. Even seaweed and aquatic tubers contributed carbohydrates and micronutrients that were scarce on the open savanna. The coastline was not just another habitat. For the humans who discovered it, it was a caloric goldmine that demanded almost none of the risk involved in scavenging on the open plains. Pay attention to this next detail because it explains everything about how the human body ended up looking the way it does. All of this raw food, the tough tubers, the stringy meat, the gritty insects, placed enormous demands on the human body, and the body adapted in ways we can literally read in the fossil record. Early hominin teeth were large, much larger than modern human teeth. The molars were broad and flat, designed for grinding rather than cutting, with thick enamel to resist the wear of processing hard, abrasive foods. The jaws were heavy and robust, attached to skull structures that provided maximum leverage for chewing muscles. A modern human skull looks almost delicate compared to a Homo erectus skull from 1.5 million years ago, and that difference is almost entirely about diet. The digestive tract was different too. Eating raw food, especially raw plant material, requires a longer gut. Plant cell walls are made of cellulose, which humans cannot digest without the help of gut bacteria, and breaking down raw starches is a slow, inefficient process. Early hominins almost certainly had larger intestines relative to their body size than modern humans do, more similar to the proportions you see in modern great apes. This brings us to one of the most fascinating ideas in all of paleoanthropology, a concept called the expensive tissue hypothesis. It was proposed in 1995 by Leslie Aiello and Peter Wheeler, and it goes like this. Both the brain and the gut are metabolically expensive organs. They consume enormous amounts of energy relative to their size. In most mammals, the size of the brain and the size of the gut are roughly proportional to overall body size. But humans broke that pattern. We have abnormally large brains and abnormally small guts. The expensive tissue hypothesis argues that this was a direct trade-off. As our ancestors gained access to higher quality food, specifically meat, marrow, and fat from scavenging and eventually hunting, they could afford to shrink their guts because they no longer needed the long digestive machinery required to process low-quality raw plants. And the energy savings from a smaller gut were redirected to the brain. In other words, eating raw meat did not just keep our ancestors alive, it literally made us smarter. The calories from animal fat and protein subsidized the growth of the most complex organ in the known universe. That is a staggering thought. The human mind, the thing that eventually produced language, mathematics, art, and technology, got its start because a small ape on the African savanna figured out how to crack open a bone and eat what was inside. You can trace this in the fossil record. Australopithecus, who lived roughly 3 to 4 million years ago and ate primarily plants, had a brain volume of around 400 to 500 cubic centimeters, roughly the size of a modern chimpanzee brain. Homo habilis, who shows the first clear evidence of stone tool use and meat eating, around 2.5 million years ago, had a brain volume of about 600 to 700 cubic centimeters. And Homo erectus, who appeared roughly 1.8 million years ago and was an accomplished scavenger and possibly early hunter, had a brain volume reaching 900 cubic centimeters or more. The brain nearly doubled in size over the same period that meat and marrow became central to the diet. That correlation is not a coincidence. But the raw diet had limits, and those limits are written in the anatomy of our ancestors. Chewing took hours. Raw meat is tough and stringy, difficult to tear apart even with stone tools. Raw tubers require sustained, forceful grinding. The caloric return per hour of chewing was relatively low compared to what cooking would later provide. And this meant that early humans were stuck in a caloric bottleneck. They could only extract so many calories per day, which limited how large their bodies and brains could grow. This bottleneck also influenced social behavior. When you spend 5 or 6 hours a day chewing, you have less time for everything else. Less time for tool making, less time for social bonding, less time for exploring and innovating. Some researchers have argued that the raw diet effectively put a ceiling on cultural complexity. Our ancestors were resourceful and intelligent, but they were trapped by the physics of their food. There is an experiment that illustrates this beautifully. Researchers have given modern humans raw wild foods, the kinds of things our ancestors would have eaten, and asked them to chew through a typical day's worth of calories. The results are always the same. Modern humans, with our small jaws and reduced chewing muscles, physically cannot process enough raw wild food to meet our daily caloric needs. We would starve. Our bodies have adapted so thoroughly to cooked food over the last few 100,000 years that going back to a fully raw wild diet is essentially impossible for us now. We are locked in. Cooking did not just change what we eat, it changed what we are. The evidence for when humans first controlled fire is surprisingly murky. You would think that fire, one of the most visible things in the natural world, would leave an obvious trail in the archaeological record, and it does, eventually. But the earliest claims are hotly debated. At the cave site of Wonderwerk in South Africa, researchers found evidence suggesting controlled fire use dating back approximately 1 million years. Burned bone fragments, ash deposits, and heat-altered sediments suggest that Homo erectus may have been using fire in this cave. But whether this was truly controlled fire, deliberately maintained and managed, or simply the result of wildfires or natural burning events, remains contested. The strongest evidence for consistent, habitual fire use appears much later, roughly 300 to 400,000 years ago, at sites across Europe, the Middle East, and Africa. By this point, Neanderthals and early Homo sapiens were building hearths, maintaining fires over extended periods, and almost certainly cooking their food. When cooking finally became routine, it changed everything. Richard Wrangham, a primatologist at Harvard, proposed what he calls the cooking hypothesis. His argument is simple but radical. Cooking is the defining technology of the human species, more important than stone tools, more important than language, more important than agriculture, because cooking fundamentally altered the caloric equation. Heat breaks down the tough cell walls of plants, making starches and sugars vastly easier to digest. It denatures proteins in meat, effectively pre-digesting them before they even enter the body. It kills parasites and pathogens, making food safer. And it reduces the time needed for chewing from hours to minutes. The result was a caloric windfall. Cooked food delivers roughly 30 to 50% more net calories than the same food eaten raw. Suddenly, our ancestors were getting dramatically more energy from the same amount of food, or the same energy from dramatically less food. And that changed everything downstream. Jaws shrank, teeth got smaller, the gut shortened. Chewing time dropped from 5 or 6 hours a day to roughly 1 hour, and all that saved energy poured into the brain, which ballooned in size over the following hundreds of thousands of years. The expensive tissue trade-off accelerated. The cultural complexity ceiling lifted. Humans could now spend their time doing something other than eating, and they used that time to develop more sophisticated tools, build social networks, create symbolic art, and eventually spread across the entire planet. Fire also transformed social life. A campfire is a gathering point. It extends the usable hours of the day past sunset, creating time for storytelling, planning, and bonding. Cooking is a communal activity that requires cooperation, food sharing, and trust. Some anthropologists argue that the campfire was the original social network, the place where language, culture, and collective identity first began to crystallize. Before fire, early humans probably slept in trees or on cliff ledges, huddled together for warmth and safety. After fire, they slept on the ground around a shared flame that kept predators at bay and held the group together. Cooking also opened up entirely new food sources. Many plants that are toxic or indigestible when raw become perfectly safe and nutritious when heated. Beans, grains, and starchy roots that would have been ignored or avoided by raw-eating ancestors suddenly became staple foods. The menu expanded enormously, and with it, the range of habitats that humans could occupy. You cannot survive a northern European winter on raw wild plants, but you can survive it with cooked grains, roasted meat, and dried, smoked fish stored over a fire. But here is the thing that tends to get lost in the excitement about fire. For every 100,000 years that humans have been cooking, there are roughly 20 times that many years when they were not. The raw chapter is not the footnote, it is the book. Cooking is the epilogue. The ancestors who cracked open marrow bones on the open savanna, who dug for wild tubers in baked earth, who shoved their hands into termite mounds, and plucked grubs from rotting logs, those ancestors built the biological foundation that made everything else possible. They developed the hands, the teeth, the guts, and most importantly, the brains that their cooking descendants would inherit and refine. Those scattered bones that Mary Leakey found in Olduvai Gorge, cut-marked and splintered, with no trace of fire anywhere near them, they are not evidence of primitive failure. They are evidence of something extraordinary, of creatures who figured out how to survive and thrive in one of the most competitive ecosystems on Earth, using nothing but rocks, sticks, and sheer persistence. Every meal you eat today, whether it is a grilled steak or a roasted sweet potato or a bowl of cereal, carries the echo of millions of years of raw eating. Your molars are smaller than they used to be. Your gut is shorter. Your brain is bigger. And every single one of those changes traces back to ancestors who never once tasted a cooked meal. They ate the world raw, and they changed because of it. We are what they ate. If this video made you look at your dinner a little differently tonight, hit subscribe and leave a comment telling us which ancient food you would have been willing to try. Smash the like button if you made it this far, and we will see you in the next one.